Well, question answering is a really big topic. And in this lecture, I will be talking about open domain question answering. And we are working on Wikipedia graph. In Wikipedia, there are hyperlinks. They are connected. When you go to hyperlink to each link, then you read it so that you can do some kind of reasoning. For example, you start from here. Then it has some hyperlink inside that reference another hyperlink. Then you go, and then now you're reasoning somehow, because now you're going how you reached one Wikipedia page from the starting Wikipedia page by going through these hyperlinks. So we have two separate problems, let's say. We have retrieval. First, we should understand which paragraph to look at, because we have millions of paragraphs. And after finding that, we can focus and just answer the question conditioned on that paragraph. So open domain question answering goes beyond just one paragraph. An open domain question answering is a task of answering a question given a large collection of text documents. So we have question, we have paragraph I, and you have seen this several times when you work with the BERT. And for example, you have question, you have your reference, and then because you know where the answer is, you know the start and end span of your answer. What is the probability of each of them? What is the probability that this one is answer? What is the probability of this start and this span is the answer, and so on. But still, do you call it reasoning chain? It's too complex. It's too expensive. It cannot be scalable. That's why researchers created this beautiful paper. Of course, knowledge graph can be expensive as well. So this paper is really interesting, because we are going to use Wikipedia links, and we jump from one hyperlink to another one, and this is called the reasoning, the retrieval. We are just retrieving, and after we have done retrieval phase, then we go to reading and answer that. So it's like expectation maximization. It's like two-stage problem solving. It's like everything. It's like decoupling a problem into two seemingly unrelated problems. So it's like separating a problem and dividing a problem into easier problems. That is called mathematical analysis. And so here, for example, you see that it's an open domain multi-hop from Hotspot QA dataset. So paragraph 2 is unlikely to be retrieved using TF-IDF retrieval due to a little lexical overlap. So we should have more mature algorithm, and this is a really mature algorithm. It constructs the Wikipedia graphs using Wikipedia hyperlink. You go from one link to the another, and so you are reasoning so you know how you arrive at a particular link, because you needed these paths to go in this direction, otherwise you couldn't find the answer. And so they look at it as a kind of sequence-to-sequence model. This is the start token, and then they say that this is, if it is A, so they should go start from A, and then now that we are in A, then we should go to B here. Then now that we are in B, we should go to D. And of course, like any sequence-to-sequence model, here to use RNN, there is a probability. What is the probability that at this time we are looking at B? And you do, for example, beam search or greedy approach to understand that. But anyway, this is just the retrieval phase. But here starts the reasoning and answering the question. Here, this part. Because now that we know which paragraph or which hyperlink to focus at, now we say what is the probability of any answer given your paragraph and the question. So there are two separate things, retrieval and reading. So we find a text in a library among billions of paragraphs, billions of hyperlink, for example. And after that, after you found that, then you zoom and the task of the reader is to obtain the likelihood of containing and extracting the correct answer phrase. And I assume that you know what are hard positive. And the graph-based recurrent retrieval needs to be trained to discriminate between relevant and irrelevant paragraphs at each step. Negative examples, for example, we use negative example along with the ground truth paragraphs. To be more specific, we use two types of negative examples: TF-IDF based and hyperlink based. For single hop question answering, we only use the type 1. For multi-hop question answering, we use both types, and the type 2 is especially important to prevent our retriever from being distracted by a reasoning path without correct answer spans. We typically set the number of negative examples to 50. So reasoning path is a sequence of paragraphs. So in our recurrent neural networks, we go from one paragraph to another paragraph until we found which paragraph is good to look at, to focus, to zoom in. And so the retrieval method learns to retrieve a set of reasoning paths to narrow down the search space. So we formulate the task by decomposing the objective into a retriever objective that selects the reasoning path relevant to the question. So now we have obtained which paragraph we need from our library. Then the reader tries to answer A. A is the answer. Finds the answer in that E that we have found. So at the same time, we want to maximize with these parameters your answer and your E sequence of paragraphs. So which sequence of paragraphs should we go? This is another problem, which is retrieval. Then after we found end of that, the last token of your recurrent neural network, then we focus on that and we answer the question. So each node is a paragraph from the Wikipedia. And so we represent every question with BERT, we represent it because for any paragraph, if for example, if I select paragraph PI, then my representation of my question is WI. And then I use this WI, I give it to a recurrent neural network because, for example, when you are going from one hidden state to another, when we are going to these units, recurrent units, for example, so I want to jump from paragraph 1 to paragraph 2, paragraph 3, and all of them have question. So I can implement this way. So there are many ways to implement this. So I move. So it's a sequence. I move from one paragraph to the other one, and I represent it with my BERT or a recurrent neural network or anything you like. So I represent it. So here are my representation. And now that I have this representation, I can just use a nonlinearity and understand what is the probability of each one. What is the probability then? So I understand that, for example, I should move from paragraph number 8 to paragraph number 6 to paragraph number 1. I know the sequence. So it's learning the sequence. And after that, we answer that. But so the loss is positive loss and negative loss as usual. So C tilde is the negative examples. This C tilde is negative examples. So this is just a retrieval. We are not reading it. We are just retrieving it here. And this is the most contribution, I think, of this paper, because we haven't used to work with sequence of paragraphs. Now we get used to it. And so the reading is, when you want to answer the problem, you need to read it so it's loss of span and loss of no answer. So we have a sequence of paragraph P1, P2, Pk. And then we share the same model for re-ranking and use the BERT's CLS token to estimate the probability of selecting E to answer the question. So at inference time, we select the best evidence, E of best, and output the answer spanned by S of read. So we found the answer, because if you know the start and end, then you know where that answer is located. So this article, I enjoyed it, very beautiful, very, very nice, elegant.